Good evening, everyone. Let's start with our project's background and goal. Full fine-tuning of large language models like LLaMA needs massive computing powers, unreachable for low-resource devices. That's why parameter-efficient fine-tuning (PFT) matters. It lets us adapt models cheaply. Our task requires ablation studies to test module effectiveness, so we compare the original LLaMA with LLaMA's adapter following standard NLP research logic. Our core goal is to verify if a lightweight adapter can truly boost LLaMA's instruction following abilities, and show it works on low-resource hardware like our GPU. Let's move to the two models we tested. Up first, our baseline, the original LLaMA 7B open resource by Matter in 2023, is a 7B parameter general language model trained on large text data with strong basic language skills. We chose 7B for balancing performance and cost to fit our GPU. We used 4-bit quantization to cut memory use, but it has a big flaw. It only does text continuations, not following instructions. For example, ask it to write a function and it might go off topic. That's why it's a perfect baseline to measure how much the adapter improves things. Now let's look at the improved models. To fix the baseline issue, we use LLaMA Adapter, a lightweight PFT method. Its core idea is to freeze all 7B parameters of LLaMA, like attention and feed-forward layers, and only add two small modules, attention gates and adapters queries. We fine-tuned just this, which are less than 1% of total parameters. This design had two big wins. It cuts training and memory costs drastically, and keeps LLaMA's original language skills while adding instruction following abilities. In short, LLaMA is the backbone. The adapters add lightweight adaptation. That's our topic and models. Next, my group member will share results and analysis.
In terms of experimental design, we select four typical tasks such as knowledge question answering and code generation, and strictly controlled variables like thermal temperatures and temperature. Regarding the experimental results, taking question 4, explain why the sky is blue as an example, we identified a key issue. Although the adapter reduced the word count by 40% and the repetition rate by 44%, the running interrupts scattering as observed. This rewards a double engaged sort effect of the PEFT method. It enhances efficiency, but it may also introduce new factual illusions. Therefore, lightweight verification is an efficient selection method, but high-risk scenarios must be combined with knowledge verification. Overall, Adapter version 1 performed positively. The average number of words decreased by 5% and the repetition rate dropped by 23%. That shows that in most tasks, its output is more concise and coherent, and its overall performance is superior to that of the base model. Facing the challenge, we choose obstacle weight inherits our tree because four-parameter filtering requires 40 GB of video memory, while there is only 8 GB locally. Meanwhile, by converting meta to Hugging Face format, the problem of out-of-memory caused by the native format not supporting 4 bits was solved. Under 8 GB of video memory, we successfully achieved a lightweight comprehension between LLaMA and Adapter version 1 through format conversion and quantization. Secondly, we found that although Adapter enhances simplicity and the completeness of some tasks, it introduced new illusions in scientific connotation, which rewards the potential risks of the PFT method. Finally, it enlightened us that the lightweight verification is an effective path for model selection, but high-risk scenario must be superimposed with knowledge validation. Thank you for listening.